Hello, ma'am.
Good evening, sir.
Yes, ma'am.
You can start, sir.
Okay, ma'am.
Good evening, sir.
Yeah, Ajay. Good evening. Only two of you are there today. Tanushree is there. Hello. Tanushree. You never talk. Huh? What we did, Ajay, last class? Yeah. Yes, Tanushree. Only text me, huh? Ajay, what we did last class? Ajay. Hello. Hello. Can you hear me, Ajay? Hello. Can you hear me? Ajay, can you hear me? Dhanlakshmi, Ritika, Tanushree, can you hear me?
Yes, sir, you're audible.
Ajay, where are you? Ajay? Yeah. See, that fellow is not here in this class. What we did last class, we were working some problem, numericals we were working, correct? I think 6 problems or something. I think we have worked till here. Based on conductance, we were working few problems. We'll work 1 or 2 more problems based on that and go to the next topic. All right. So we learned conductance. Now, conductance is the reciprocal of resistance we learned, but we also learned what is molar conductance, equivalent conductance, the relation between specific conductance and equivalent conductance, the relationship between specific conductance and molar conductance, all that we learned. Now, you should answer me this question. Now, I take a conductivity cell like this. I have 2 electrodes here. I have 2 electrodes connected to the power supply. We have some electrolyte into it. The distance between the 2 electrodes is 1 centimeter. The distance between these 2 electrodes is 1 centimeter. And area of cross-section area is 1 centimeter square. Now, conductivity of all the ions present in the solution between these 2 electrodes of 1 centimeter and length 1 centimeter or distance 1 centimeter and area of cross section is 1 centimeter square. Those kind of conductance is called a specific conductance. Now, conductivity of 1 molar solution overall will be called as molar conductance. Now, this is an important question. What happens to specific conductance on dilution? What happens to molar conductance on dilution? Tell me what will happen to specific conductance on dilution. Specific conductance on dilution. Whether specific conductance on dilution, specific conductance will increase or decrease or remain same. Please tell me, participate in the class. Hello, are you there?
Specific conductance with
Dilution.
so
I was
so
calling
specific.
you 10 times. Where were you that time? 2 minutes before, where were you in the class? You were not there. You didn't answer me. Ajay. Hello?
So
Yeah.
sir, I lost connection momentarily, sir.
Huh?
So I lost connection, sir.
Yeah, when we ask questions, you will lose connection, man. Correct. Now tell me what will happen to specific conductance on dilution? Anybody? Ajay, tell me. What will happen to specific conductance on dilution? Already, I clearly told you conductance or specific conductance is nothing but the conductivity of ions present between the electrodes of 1 centimeter length and area of cross section is 1 centimeter square. Now,
Sir,
when you
it's inversely proportional, sir. It decreases, sir.
Yes, specific conductance is inversely proportional to dilution. That means when you dilute, the ions from here will move out. It will the same number of ions will not be here. Therefore, what happens is specific conductance decreases on dilution, or we can say specific conductance is inversely proportional to dilution. As dilution increases, specific conductance decreases. Now, what happens to molar conductance? It's an important question. Molar conductance. What happens to molar conductance on dilution? Molar conductance on dilution remains almost to what? Same. Why? Because conductivity of 1 mole of ions, irrespective of dilution, the number of ions remains the same. Therefore, molar conductance remains almost the same in case of what? Dilution. Did you follow these 2 points?
Yes, sir.
Yes. Now, the 7th question, we'll work some of the problems again and continue to the next topic. Now, specific conductance of 0.1 molar sodium chloride is 1.01 in 10 to the power minus 2 per ohm per centimeter. Specific conductance kappa is 1.01 into 10 to the power minus 2 ohm inverse centimeter inverse. They are given the concentration of the electrolyte. They've given 0.1 molar NaCl. They're asking you to calculate molar conductance. So what's the relation between molar conductance and specific conductance? Lambda is equal to K into 1000 by molarity or concentration. Molarity or kappa is 1.01 into 10 to the power minus 2 into 1000 divided by concentration is 0.1. 0.1. On simplification, the answer we will get is 1.01 into 10 to the power minus 2 ohm inverse centimeter square per mole. So therefore, the answer for this question is option A, 1.01 into 10 to the power 2, not minus 2, it is 2. Sorry, I mentioned minus 2, it's wrong, it's 2. So you can write this as what, 10 to the power 3. This is 10 to the power minus 1. You can write like this, 1.01 into 10 to the power minus 2 into 10 to the power 3 divided by 10 to the power minus 1. So when this minus 1, 10 to the power minus 1 goes to numerator, what 10 to the power plus 1. So 10 to the power 4, 10 to the power 4, 10 to the power minus 2. So what happens? It is 10 to the power plus 2. The answer you'll get is 10 to the power plus 2, 1.01 10 to the power plus 2. Therefore, the answer for this question is option A. The next question, the molar conductivity of 0.5 mole per decimeter cube solution of silver nitrate with electrolytic conductivity of 5.76 into 10 to the power minus 3 Siemens centimeter inverse at 298 Kelvin is. What is that they're asking? They're asking you to calculate molar conductivity. So what is that they've given? Concentration they've given us 0.5 mole per decimeter cube. And they've given something called as electrolytic conductivity. Now, what is this electrolytic conductivity? What is this electrolytic conductivity? This electrolytic conductivity is kappa. Why it is kappa? You can see the unit. It is Siemens per centimeter, per ohm per centimeter. So looking at the unit, you can tell what kind of conductivity they have mentioned. So it is Siemens centimeter inverse, that is per ohm per centimeter is specific conductance, kappa. It is 5.76 into 10 to the power minus 3 Siemens centimeter inverse. So what will be that lambda now? Lambda, same formula. It is kappa into 1000 divided by lambda. It is equal to 5.76 into 10 to the power minus 3 into 1000 divided by 0.5. On simplification, the answer what we will get is 11.52 Siemens centimeter square per mole. Siemens centimeter square per mole. See here, you should ask me a question, why they have given temperature? Here, temperature has no roles, right? Therefore, to confuse you with the question, they've given you the temperature. The next question, and then we will go to the next part of the topic. The next question, resistance of 0.2 molar solution of electrolyte is 50 ohms. So resistance they've given us 50 ohms. And also they've given you the concentration to be 0.2 molar. Resistance of 0.2 molar solution of electrolyte is 50 ohms. The specific conductance of the solution, they've given kappa, specific conductance 1.4 Siemens per meter. This is first part. The second part is the resistance of 0.5 molar solution of the same electrolyte is 280 ohms. The molar conductivity of 0.5 molar solution of the electrolyte in Siemens meter square per mole is. Now from this data, we can calculate the cell constant. Kappa is equal to L by A into 1 by R. Specific conductance or conductance is inversely proportional to resistance. So conductance is directly proportional to length and inversely proportional to A. So they have given specific conductance as 1.4, length by A they have not given, resistance they have given to be 50. Therefore 1 by 50. So L by A will be 1.4 into 50. That will be equal to 70 per meter. This L by A is called a cell constant. This L by A is called as what? Cell constant. Now in the second case, what they've given, L by A for a same electrolyte. The electrolyte is same, therefore L by A, the cell constant will remain same. L by A is 70 per meter. So in the first data, whatever is given, we calculated what? The cell constant L by A. In the second case, what they've given, the concentration they've given us 0.5 molar. And also they've given resistance to be 280 ohms. The molar conductivity they're asking, molar conductivity of this solution. So resistance is equal to rho into L by A. Rho is called as resistivity. Or we can write 1 by rho is equal to 1 by R into L by A. So that is equal to 1 by 280. Resistance is 280 into L by A is 70. So 1 by rho is equal to 0.25 Siemens centimeter inverse. So 1 by rho is 0.25 Siemens centimeter inverse. Now they're asking you to calculate molar conductivity. In order to calculate molar conductivity, lambda is equal to kappa into 1000 divided by C. So kappa is point, or we can write this lambda also, we can write it as kappa into Siemens per meter divided by 1000 liter per meter cube into molality. So we can write this also because concentration is inversely proportional to volume. So we can write this. So when you write this, I'll write the substitution here. Lambda will be 0.25. We found out here, divided by 1000 into 0.5. So on simplification, you'll get 5 into 10 to the power minus 4 Siemens meter square per mole. So therefore, the answer for this question is option B, 5 into 10 to the power minus 4. So other questions. See here, this question, what we learned now. Water is added to aqueous solution of an electrolyte. What is the change in specific conductance? So specific conductance will what? Decrease. Decrease. Yeah, we learned it. We learned all this, So we'll continue with one more problem is there. That's all. And an increase in equivalent conductance of strong electrolyte. An increase in equivalent conductance of strong electrolyte with dilution is mainly due to. See, strong electrolyte I have already dissociated. Strong electrolyte is already dissociated. But on dilution, still the conductivity increases. Why they're asking? Conductivity is not only the number of ions, but other factors, mobility of the ions also matters. So on increasing the dilution, the increase in the ionic mobility also increases. See, since it is a strong electrolyte, it is 100% ionized. No doubt about it. So on dilution, what happens is speed of the ions which moves will increase. Therefore, conductivity increases. Therefore, the answer for this question is option A. All right. So the next part of the topic we will learn. I think conductivity, we have learned it in detail. Now, Cold-Rush's law, you have to pay attention. This is not for strong electrolytes. So Cold-Rush's law is for weak electrolytes. In general, it is for weak electrolyte. Cold-Rush is the name of a person. Kohlrauschs. Cold-Rush's law. What does this Cold-Rush's law states? At time infinite dilution, the molar conductivity of an electrolyte can be expressed as the sum of the contribution of its individual ions. And the statement is very confusing, but anyways, we will try to understand this. Now, why do we talk about infinite dilution? Now, at minimum dilution, strong electrolyte will undergo dissociation completely, no doubt about it. At infinite dilution, even the weak electrolyte is expected to undergo ionization 100% or completely. Therefore, at infinite dilution, the weak electrolyte also will behave like strong electrolyte. So I just told you Cold-Rush's law is applicable for weak electrolytes. What it says is, at infinite dilution, the molar conductivity of an electrolyte can be expressed as the sum of the contributions from its individual ions. So lambda infinity, lambda is conductivity, molar conductivity at infinite dilution is equal to V into, or V plus. What is this V plus? It's not V plus here, it is V plus lambda plus infinity plus of V minus lambda minus infinity. What is this? All right, now this V plus is the valency of the cation. All right, and V minus is the valency of the anion. So we can write it as lambda infinity is equal to V plus lambda plus at infinite dilution plus of V minus into lambda minus at infinite dilution. This is the representation of Cold-Rush's law. Here it is a little confusing. Lambda infinity, molar conductance at infinite dilution is equal to the sum of contributions from its individual ions. Now, V plus and V minus are number of cations and anions per formula unit of electrolyte respectively, and lambda plus infinity and lambda minus infinity of molar conductivities of cation and anion at infinite dilution respectively. The use of above equation in expressing the molar conductivity of an electrolyte is illustrated as the molar conductivity of HCl at infinite dilution can be expressed. See, HCl is a strong electrolyte, but to understand the Cold-Rush's law, we have taken this as an example, assuming this HCl undergoes complete dissociation. Lambda not HCl, lambda not indicates what infinite dilution. So we can write it as lambda infinity or lambda naught. Okay, lambda naught is at infinite dilution. That will be equal to, see, HCl is a strong electrolyte. It will dissociate completely to form H plus and Cl minus. Okay, so conductance of H plus ions and conductance or conductivity of Cl minus ion. The sum of the conductivities of H plus and Cl minus ions gives you the overall molar conductivity of HCl. So this is Cold-Rush's law. What is important question? Cold-Rush's law application we will learn in a few minutes time. What is the statement for Cold-Rush's law? At time infinite dilution, the molar conductivity of an electrolyte can be expressed as the sum of the contributions from its individual ions. Sum of contributions from its individual ions. Now, for an example, one more example we will take. Now, if you take barium chloride, now barium chloride contribution, now lambda naught of barium chloride will be equal to lambda naught of barium 2 plus what is the barium? We have only one ion because this will dissociate to form barium 2 plus 2 Cl minus. So it will be 2 into lambda naught of Cl minus. So the number of anions is 2 as per the equation. Cation is 1, so you write it doesn't matter here. So V plus V minus stands for number of cations and number of anions in the Cold-Rush in the equation what we learned in the earlier here we learned it. This V plus stands for number of cations, V minus stands for number of anions. That is what I've written. Did you follow what is Kohlrausch's law? Students, did you follow?
Yes, sir.
Yes. Now, what is the applications of Kohlrausch's law? It is possible to calculate the limiting molar conductivity of any electrolyte by knowing the molar conductivity of the ions. So it is possible to calculate the molar conductivity of any electrolyte. Molar conductivity of any electrolyte by knowing the limiting molar conductance. What is this limiting molar conductance? Limiting molar conductance is nothing but conductance at infinite dilution is called as limiting molar conductance. Lambda naught is called as limiting molar conductance. Lambda naught is called as what? Limiting molar conductance. Or conductance at infinite dilution. The second application is it is possible to calculate the dissociation constant of weak electrolyte by knowing the value of limiting molar conductivity and molar conductivity of for a given concentration. For a given concentration. So these are the applications of Kohlrausch's law. The first one is it's possible to find calculate the molar limiting molar conductivity of any electrolyte by knowing the limiting conductivity of the ions. For an example, it is very simple. For an example, if I take NaCl, it will dissociate to form Na plus and Cl minus. What is lambda naught of M, NaCl? Lambda naught of N. Lambda naught is nothing but limiting molar conductivity of an electrolyte. That will be equal to lambda naught of Na plus lambda naught of Cl minus. This is the first application. First application. When we know the limiting molar conductivity of each ions, we can find the limiting molar conductivity of the electrolyte. The second one is it is possible to calculate the dissociation constant of a weak electrolyte by knowing the value of limiting molar conductivity for a given concentration. See, degree of dissociation or dissociation constant of weak electrolyte is represented by letter alpha. Alpha is equal to lambda m divided by lambda naught. Lambda naught m, like this. Now, what is this lambda m? This is molar conductivity at a particular concentration. At a particular concentration. And lambda naught m is molar conductivity at infinite dilution. Infinite dilution. So this is the formula to calculate the degree of dissociation. One is degree of dissociation is calculated by the formula lambda m divided by lambda naught m. The second one, the second formula is we can calculate the dissociation constant. Ka is equal to C alpha square divided by 1 minus alpha. If you know the alpha value, 1 minus alpha, if you know the degree of dissociation, we can calculate the dissociation constant. Ka, dissociation constant is given by the formula C alpha square divided by 1 minus alpha. This formula is written as C lambda m square divided by, this is substituting what is alpha. Alpha you substitute this values, if you substitute and simplify, you get this equation C lambda m square into lambda naught m into lambda naught m minus lambda m. So you can calculate the formula, dissociation constant. Ka is called as dissociation constant of a weak electrolyte. I told you Kohlrausch's law is applicable for weak electrolyte. So Ka, dissociation constant, can be calculated by the formula C alpha square divided by 1 minus alpha, or that is equal to C lambda m square divided by lambda naught m into lambda naught m minus lambda m. What is this lambda naught m? What is this lambda naught m? What is this lambda naught m? Students, are you there?
Sir, it's at infinite dilution, sir.
Tell me. What is lambda naught m?
Sir, at infinite dilution, sir.
What is lambda naught m?
Sir, the molar conductivity has infinite dilution, sir.
Yes, lambda naught is molar conductivity at infinite dilution. And lambda m is?
Sir, it's at a particular concentration, sir.
Yes, conductivity at a particular concentration. All right. Students,
Yes, sir.
others are there? Yeah. Others?
Yes, sir.
So formulas you remember. Now see here, variation of molar conductivity with concentration. Molar conductivity, variation of molar conductivity with concentration. This is an important question for your 12th standard. All right. In case of strong electrolyte, the first one is for strong electrolyte. Molar conductivity increases slowly with dilution, which can be identified using the following expression. See, strong electrolytes already they are what? Dissociated completely. But on dilution, what happens? The mobility of the ions increases. Therefore, conductivity increases. That is why it says molar conductivity increases slowly with the dilution, which can be identified using the following expression. Lambda m is equal to lambda naught m minus a into root c. Lambda m is conductivity, molar conductivity at a particular concentration. Lambda naught m is molar conductivity at infinite dilution. A is a constant, square root of c. C to the power 1 by 2 otherwise. See, when a graph is plotted, lambda m versus c 1 by 2, we get a straight line with the intercept to lambda naught m and slope equal to minus a. We will learn this graph. I don't know whether it's represented here. The graph is not represented. I will draw the graph. Now, now when you draw the graph like this, that is lambda m versus c1 by 2. C1 by 2, you get a straight line like this. This intercept is equal to lambda naught m. And the slope is equal to minus a. The slope is equal to minus a. So this equation, this minus a in this equation is the slope, and lambda naught m is nothing but the intercept of the graph. So when you plot lambda m versus square root of c, or square root of c is nothing but c to the power 1 by 2. So you get a straight line like this. So intercept lambda naught m is from the, you get lambda naught m from the intercept, and from the slope you get the minus a value. The value of A for a given solvent and temperature depends on the type of electrolyte. So A is not constant for all the electrolyte. A really varies from the solvent and the temperature of the electrolyte. That is charge on the cation and anion produced on dissociation of the electrolyte in the solution. So either A value depends on the given solvent and temperature on the type of the electrolyte. That is charge on the cation and anion produced on dissociation of the electrolyte in the solution. Next is, this is for strong electrolyte. For weak electrolyte, the molar conductivity increases with dilution. We learned weak electrolyte will undergo more dissociation on dilution. So therefore, molar conductivity increases on dilution, because on increase in the degree of dissociation and the number of ions in total volume of the solution that contains 1 mole of an electrolyte. So here molar conductivity increases with dilution because of the increase in degree of dissociation. That means as you dilute, the number of ions dissociating will increase. Number of molecules dissociating will increase. Number of ions formed will increase. Therefore, molar conductivity also will increase. It is noted that at lower concentration, the molar conductivity increases steeply, thereby limiting molar conductivity of weak electrolyte cannot be calculated accurately. So at lower concentration, molar conductivity will increase steeply, thereby limiting molar conductivity of weak electrolyte cannot be calculated accurately. At infinite dilution for weak electrolyte, dissociates completely. That is, At zero concentration, the dissociation of weak electrolyte is equal to 1. See, at the statement you have to understand, at infinite dilution, all the weak electrolyte will dissociate completely. That is, at zero concentration. So at infinite dilution, the concentration of a solution will be with zero, almost zero. Therefore, we say at zero concentration, the dissociation of weak electrolyte is equal to 1. That means it completely dissociates. Therefore, the dissociation of weak electrolyte is equal to 1. I don't know how many people understood this statement. See, at infinite dilution, for weak electrolyte, dissociates completely. So weak electrolyte will increase their dissociation on dilution. At infinite dilution, when you take excess of solvent, all the weak electrolytes will undergo complete dissociation. So when all the weak electrolyte undergoes complete dissociation, and if the solvent concentration is more, dilution is extremely high, the concentration of the solution is considered almost to be what? Zero. When the concentration of the solution is almost considered to be zero, at that state, we take degree of dissociation of weak electrolyte to be equal to 1. Did you follow this, students?
Sir, so the maximum degree of dissociation a weak electrolyte can have will be 1, sir.
No, see here, it means like this. It means like this. If I take one molecule of HCl, and this one molecule of HCl will dissociate completely to form H plus and Cl minus. It's a strong electrolyte. So I have taken one molecule of HCl, and all the one molecule dissociates. Therefore, what's the ratio? Ratio is 1. Likewise, if you take a weak electrolyte, this weak electrolyte at infinite dilution, it is assumed to be what? Completely dissociated. See here, only one-sided arrow mark I've written, even though acetic acid is what? A weak acid. At what dilution this is? Infinite dilution.
Yes.
So therefore, we take it to be what? 1. The dissociation of weak electrolyte is equal to what? 1. We assume it to be completely dissociated and equal to 1. Did you follow this?
Yes, sir.
Now, see this formulas I gave you now. Just now I gave you in the application. If C is any concentration, alpha is the degree of dissociation, which is the ratio of molar conductivity at a particular concentration to the limiting molar conductivity. What do you mean by limiting molar conductivity? Conductivity at infinite dilution is called as limiting molar conductivity. See, this not indicates infinite dilution, lambda naught m. So, but for a weak electrolyte, the degree of the dissociation constant is given by the formula. We learned it now. Ka is equal to C alpha square divided by 1 minus alpha. If you substitute for alpha lambda m divided by lambda naught m and simplify, we get this equation C into lambda naught m divided by lambda naught m into lambda naught m. This is lambda m, it's not lambda naught m. Lambda m divided by into what? Lambda naught? Lambda m square it is. It's not lambda m square into lambda naught m minus lambda m. We learned it here. This is a printing mistake. See, we wrote it here. C into lambda square m divided by lambda naught m. The same thing is represented here also. All right. So this is based on Kohlrausch's law. Kohlrausch's law. Did you understand?
Yes, sir.
See, this equation is called as Debye-Huckel's. Debye-Huckel's. D-E-B-Y-E. Debye-Huckel. H-U-C-K-E-L. Debye-Huckel Onsager equation. Lambda m is equal to lambda naught m minus a into c to the power 1 by 2 or root c. This is called as what? Debye-Huckel Onsager equation. So we'll work out some of the problems based on Kohlrausch's law. Little confusing. Anyways, we will do it. At 18 degrees Celsius, the conductance of H plus and CH3CO minus at infinite dilutions are 315 and 35 mho centimeter square per equivalence. Mho is nothing but per ohm. OHM is ohm. MHO is mho. Inverse of mho is ohm is called as what? Mho. All right, centimeter square per equivalence respectively. The equivalent conductivity of acetic acid at infinite dilution is, according to Cold-Rush's law,
So we just
conductivity
need
of,
to add both sides. So
that's
315
all.
plus 35.
Yeah, it
So
will be what?
356.
Lambda of H plus of what? Lambda of CH3CO minus. And this is 315 plus 35. It is 350 more meter square per equivalence, centimeter square per equivalence. All right, this is simple. This is simple because we know that acetic acid will dissociate to form acetate ion and H plus ion. Therefore, Cold-Rush's law clearly states that conductance of an electrolyte. Here, it is possible to calculate the limiting molar conductivity of any electrolyte by knowing the limiting molar conductivity of the ions. Or we learned it here, the definition. At infinite dilution, the molar conductivity of an electrolyte can be expressed as sum of the contribution from its individual ions. So here, what's the individual ion? Acetate ion and H plus ion. So contribution of H plus ion and contribution of acetate ion, when you sum it up, then you will get the molar conductivity at what dilution? At infinite dilution. The first question, the answer for this is 350. Students, did you follow?
Yes, sir.
Yes, sir.
The next question, limiting molar conductivity of NaBr is. Limiting molar conductivity of NaBr is. Just observe. Now NaBr, now just see the second option. Lambda naught M NaBr is equal to lambda naught M NaCl plus lambda naught M KBr minus lambda naught M KCl. So lambda naught, this will be what now? Can I write lambda naught M of Na plus lambda naught M of Cl minus, because the NaCl will dissociate to form what? Na plus and Cl minus, individual ions according to Cold-Rush's law. Yes or no?
Yes, sir.
Plus
Yes,
lambda
sir.
naught M of K plus lambda naught M of Br minus of lambda naught M of K plus lambda naught M of Cl minus. So on addition of all this, what you will get, you see, what will happen? This is plus MCl, all right, plus MCl, and here it is minus MCl. So these two will get cancelled. These two will get cancelled. And we have plus MK plus, and here you have minus MK plus. This also will get cancelled. What is left out? Lambda M Na plus what? Lambda naught M of what? Br
So Br
minus.
minus.
So that means you're getting the molar conductivity of what? Sodium bromide. So
Yes.
this is for weak electrolytes. We can find, we'll work some of the problems based on this in a few minutes time. I hope so. Therefore, the answer for this question is what? Option B. Option B. See, if you take NaOH, OH minus will be there. And Br will be there, Cl minus will be there. Nothing will get cancelled here. So you will not be getting what? NaBr. And here you can see Na is there, Na is here also, Cl. There is nothing will getting cancelled. So you will not get NaBr. So, but when you take NaCl, KBr minus KCl, you can see that finally we arrive at lambda naught M of what? NaBr. Correct?
Yes, sir.
Yes, sir.
The third question, what will be the molar conductivity of Al3 plus ions at infinite dilution if the molar conductivity of Al2SO4 thrice is 858 Siemens centimeter square per mole, and ionic conductance of sulfate is 160 Siemens centimeter square per mole at infinite dilution. Now, can I say lambda naught M of Al2SO4 thrice is equal to?
So we need to subtract it, right, sir?
No, we will work out this. This is simple. Just follow this. Now, firstly, we should know that Al2SO4 thrice will dissociate to form 2Al3 plus plus 3 SO4 2 minus. So we can write lambda naught M of aluminum sulfate will be equal to lambda naught M of, we can 2 into lambda naught M of Al3 plus of 3 into lambda naught M of SO4 2 minus. We want lambda naught M of aluminum. So if I take it to this left side, we'll get lambda naught M of Al2 SO4 thrice minus 3 into lambda naught M of SO4 2 minus will be equal to what now? Lambda naught M of Al3 plus 2 into lambda naught M of Al3 plus. So therefore, what will be lambda naught M of Al3 plus?
So 858 minus 480 divided
By 2, correct. So it will be what? 858 minus 3 into 160.
That's
3 into
480.
160, yeah, divided by 2. So what will be the answer you will get? You will get around 189 Siemens centimeter square per mole. The answer for this question is option A.
Okay, sir.
Option A. The next question. The equivalent conductance of barium 2 plus and Cl minus are 127 and 76 per ohm centimeter square per equivalence at infinite dilution. What will be the equivalent conductance of barium chloride at infinite dilution? Lambda naught of barium chloride will be equal to what? Lambda naught of barium 2 plus 2 into lambda naught of Cl minus, because each barium chloride will give 2 chloride ions. Therefore, it will be 2 into lambda naught. That will be equal to 127 plus 2 into 76. So that will be equal to 279 ohm inverse centimeter square per equivalence. Now, see, this is lambda stands for molar conductance. Now they're asking you to calculate the equivalent conductance. So equivalent conductivity will be equivalent conductance or conductivity will be equal to 279 divided by 2, half, because 2 chlorine atoms. So divided by 2 will be equal to 139.5 ohm inverse centimeter square per equivalence. So the answer for this question is option A, 139.5. See, there's a confusion here. They're asking you to calculate the equivalent conductance. If you leave it here, it is molar limiting conductivity. So 279 per ohm centimeter square per equivalence will be equivalent molar conductivity. In order to find the equivalent conductivity, you have to divide it by 2. Therefore, the answer for this question is 139.5. Next question. Molar conductivity of 0.025 mole per liter methanoic acid is 46.1 Siemens centimeter square per mole. The degree of dissociation and dissociation constant will be given lambda naught H plus is 349.6 Siemens centimeter square per mole, and lambda naught HCO minus is equal to 54.6 Siemens centimeter square per mole. Now, what is methanoic acid? What's the chemical formula of methanoic acid? Anybody? What's the common name for it?
CH3COOH.
CH3COH is ethanoic acid, acetic acid.
So HCOOH.
Sir, HCOOH.
HCOH. This is formic acid. Methanoic acid, commonly called as formic acid. So lambda naught of formic acid will be equal to lambda naught of H plus lambda naught of HCOO minus. H plus ion and format ion, it will dissociate. H plus ion, what they have given conductance? They have given us what? 349.6. Plus for format ion, they have given 54.6. That will be equal to 404.2 Siemens centimeter square per mole. 404. It's addition. Now, what they're asking you to calculate? They're asking you to calculate degree of dissociation and dissociation constant. What's the formula to calculate degree of dissociation? Lambda alpha is equal to lambda m divided by lambda naught m. Lambda m, what they've given? They've given molar conductivity of 0.025 mole per liter methanoic acid, that is 46.1. And Lambda naught m we found out. It is 404.2. So on simplification, you will get it as 11.4 in some, into percentage. So you have to multiply this and you get the value 11.4%. You'll get 0.114 multiplied by 100. So you'll get it as 11.4%. So the answer is option A. But the second part of the question also they've asked, Ka is equal to, what is Ka? C into alpha square divided by 1 minus alpha. C is 0.025. They've given the concentration. Into alpha is 0.114 the whole square. Here we have taken it in percentage, but actually the value is what? 0.114 divided by 1 minus 0.114. On simplification, we will get it as 3.67 into 10 to the power minus 4 mole per liter. So therefore, the answer for this question is option A. Just go through this problem. If you have any clarification, you can ask with this problem quickly. Any confusion with this problem? No? No?
No, sir.
Yeah.
Yes,
The
sir.
next question is also a simple question. Wait. The equivalent conductivity of n by 10. N by 10 is 1 by 10. Solution of acetic acid 25 degrees Celsius is 14.3 into per ohm centimeter square per mole. What will be the degree of dissociation of acetic acid? They have given lambda infinity, they have given. So lambda infinity of acetic acid they have given us 390.71, and lambda at 0.1 concentration, at a particular concentration they've given lambda C, they've given as 14.3 per ohm per centimeter square per equivalence. What is degree of dissociation? It is lambda at a particular concentration divided by lambda not m. This is m. So it will be 14.3 divided by 390.71. That will be equal to 0.0366. It is 3.66%. 3.66%. It's a very simple problem. The answer for this question is option A. The next question. Weak monobasic acid is 5% dissociated. A weak monobasic acid is 5% dissociated in 0.1 mole per decimeter cube solution. Limiting molar conductivity of acid at infinite dilution is 4 into 10 to the power minus 2 per ohm meter square per liter. What will be the conductivity of 0.05 mole per decimeter cube solution of the acid? So we can write Ka is equal to C into alpha square divided by 1 minus alpha. Alpha is very, very small. Therefore, we can neglect and write K is equal to alpha, C into alpha square. That is equal to concentration they've given us 0.01, and they've given us 5% dissociated. 5% dissociated means it's 0.05 the whole square. So we get Ka value. This is Ka. On simplification, you will get the value 2.5 into 10 to the power minus 5. Now simplify this, 2.5 10 to the power minus 5. From this, we can calculate 2.5 into 10 to the power minus 5 will be equal to 0.01 into alpha square, or alpha square will be 2.5 into 10 to the power minus 5 divided by 0.01. So on simplification, we will get alpha to be 0.0223. Alpha will get us what? 0.0223. So therefore, what is the degree of dissociation? Lambda m divided by lambda naught m, that is equal to, or maybe we can write lambda m is equal to alpha into lambda naught m. Alpha is 0.0223. Lambda naught m is 4 into 10 to the power minus 2. They have given you here. Molar conductivity at infinite dilution, 4 into 10 to the power minus 2. So on simplification, the answer we will get is 8.92 into 10 to the power minus 4 ohm inverse centimeter square per equivalence. Per mole. So the answer for this question is option B, 8.92 into 10 to the power minus 4 ohm inverse centimeter square per mole. Can we continue the class in the next? Other few problems we'll do because it's a lengthy problem. I require a little time for explanation. We'll continue 2 more problems based on this, and the next topic will go in the next class. That is tomorrow we will do it. Is it fine? Is it fine?
Yes, sir.
Madam, I'll stop the class, ma'am. Ma'am? Hello, ma'am?
Yes, yes, sir. Sorry, sir. I put it in mute and then I was talking. Sorry.
No,
Yes, sir.
Bye.
Thank you, sir.
Bye.